All right, day 9, kinematics. Uniform and non-uniform motion. In uniform motion, the velocity is constant. For instance, every second an object travels 20 centimeters. That would be one example. Another example. Let me get my pen here. Blue. Is that my color? Blue? That'll work. If you're going in the speed limit and it's 30 miles an hour, that means you're going to travel 30 miles in every hour. Or gravity being, in English units, 32 feet per second squared. That's a little bit different because that's a acceleration. We'll get there later. But either way, it's something per something. It's a division problem. So non-uniform motion, the velocity is not constant, but it's changing. So I jumped ahead here. This would be a non-uniform motion because this is the acceleration of gravity due to the Earth's gravitational pull, and you actually speed up by 32 feet per second every second. So that's non-uniform motion. You're speeding up or slowing down more or less. So if you look at a graph, whenever your graph position first time, and there's nonlinear path to the motion is not uniform. So if this were uniform of the meters per hour versus days, it would be a straight line. That's uniform. Is the straight line. But if it's curved, it's going to be non-uniform motion. So in my example, say non-uni, in my example, it looks like that the number of meters per hour kind of sharply increases, but starts to decrease slowly over time. And in fact, if we extrapolate this below zero, it's coming from near an infinite point. So this is an example of what we call slowing down. And when you slow down, the absolute value of your slope, so m would be slope, the absolute value of your slope would be decreasing. And more on that in a little bit. But this is slowing down because while it does have curvature, it's getting less and less. So your slope is decreasing and decreasing and decreasing. The object in this case is speeding up because the displacement for each successive time interval is increasing. Another way of knowing if something is speeding up or slowing down is by looking at the slope. If I were to find the slope at this point, it looks like this. At this point, it looks like this. At this point, it looks like this. This point it looks like this, and then so forth. So the slope is getting steeper and steeper, and that's how we know it's speeding up. Whereas in this example, the slope was pretty steep right here, less steep right here, even less steep right there, and barely any steepness there. And so that's why it's slowing down, is because the steepness of the slope is decreasing. And also another thing, the object in this case is moving in the positive direction. We know that because it starts at 0 and it's going towards, I guess in this case, 60. And so the overall displacement will be positive. So a good example of this would be like a car speeding away from you. From you, if you are the origin. So, graph. Another example of speeding up, and I kind of got cut off there. Sorry about that. Is this graph right here. This is, I just made up these values, but this is the position versus time in AUs, which are astronomical units. An astronomical unit, it's not necessary to know this for the class, but I'm just kind of telling you. It's the sun to Earth distance. And so we measure things in the solar system using AUs, astronomical units, because the solar system's huge. Well, anyways, this is a solar sail, and so I chose this graph originally for this reason alone. Basically, solar sails are really tiny satellites that, when they go into orbit, have a very, very thin sail-like feature that spreads out. What's kind of cool is you're thinking, well, how can you sail when there's no wind in space because there's no air? True, but there are photons. Photons are individual particles of light. While photons have no mass, they do have momentum. And so the actual over time of all the photons hitting the solar sail will actually carry it, and it will speed up and speed up and speed up. And so it will move away from us, but I would say you're kind of thinking backwards, because we would say going toward the sun would be forwards. And so in this case, the sail is speeding up as well. And the reason it's speeding up is because it's the absolute value of its slope is increasing as it moves away from us. And this is exactly what would happen with a solar sail. More photons would hit it, and once in motion, always in motion. And if you have a force applied to it, your acceleration is going to remain constant. Fun facts about the solar sails that you never really think of, and is that, yeah, you could take a solar sail, let's say, I don't know, Alpha Centauri, 4.3 light years away. And then, if you wanted to stop, then that's the problem. It took you probably not 4.3 years, but like 80 years to build up that kind of speed. And then that point, it's like, how do you stop? And they're trying to figure out ways of actually doing that. Because if you stop, then you can check out what's there, see if there's any life, et cetera, et cetera. And slowing down, this is another example of a graph slowing down. In this case, it slows down because the absolute value of the slope gets less steep and less steep to the point where it's practically has no steepness. So this would be an example of a slowing down graph. And it's moving towards you, so it would be like a dog running towards you, but slows down right before it gets to you. All right, I believe that is it for day 9. I will see you in class today.